All right, so now we're going to look at the discrete Euler-Lagrange maps in terms of the discrete Legendre transforms. Okay. All right, so let's just recall the setting. You're given a discrete Lagrangian, LD, which is a map from two copies of the configuration manifold to the rails, right? And then we have discrete Legendre transforms. And there are two of them. Okay. So there's F plus LD, which maps Q0, Q1 to Q1, D2, LD, Q0, Q1. Right, and if you recall, it's like this is derivative with respect to the second slot. The thing in the second slot is Q1. It's a derivative of LD, Q0, Q1 with respect to Q1 here. Right, and then there's F minus LD, also applied to Q0, Q1. This is Q0 minus D1 LD, Q0, Q1. Okay, all right, so discrete Legendre transforms. And then the claim is that you have the following diagram. So you consider the following commutative diagram. The fact that this is a commutative diagram is not so difficult to show. You can either sort of do this by basically defining it's like some of the maps. It's like in order to, well, defining maps in such a way that the diagram commutes, and then showing that those maps are related to the discrete Euler-Lagrange maps and the discrete Hamiltonian maps. So that's what we're going to try to do. All right, so you have the following diagram. It says, which involves, first we're going to fill in the discrete Legendre transforms. Okay, so we have Q0, Q1, right? And I can do two things to it. I can apply F minus LD. This gives me Q0, and it's natural to interpret this as as P0, right? So it's going to be Q0, P0, all right? And then I can do F plus LD to this, and this is Q1, and it's natural to interpret this thing as P1. So this is Q1, P1, and then I can do the same thing for Q1, Q2, and this is F minus LD, and then this F plus LD maps to Q2, P2. All right, so far I've not really done anything. There's the diagram trivially commutes because there are no closed loops. All right, so what we're going to do is we're going to fill in this diagram with a bunch of maps. Okay, and then there, one has to check that this still gives you a commutative diagram. And the way I'm going to propose to do that is to show that those maps are sort of the maps which we care about. It's like for the discrete Euler-Lagrange maps and discrete Hamiltonian maps. So I'm going to denote this by F sub LD, and then this is F tilde sub LD, right? All right, and then these are defined, it's like so that the diagram commutes, okay? So the discrete Legendre, so the discrete Lagrangian map, okay, which I called F sub LD, right? It's a map from, and I should say what it is. It's defined to be whatever makes this diagram commute. So if I want to go from here to here and I want it to commute, then I have to think of it as the composition of FLD plus with the inverse of FLD minus. Okay. All right. So F minus LD inverse composed with FLD plus. Okay. All right, so that's what it is. Okay, is a map from Q cross Q to itself. All right. Okay, and the way you should sort of think about it is that it maps pairs of points Q0, Q1 to Q1, Q2. All right. And so if you recall, it's like the form of the discrete Euler-Lagrange equations, right? Discrete Euler-Lagrange equations said something like, so discrete Euler-Lagrange said that d2 LD Q0 Q1 plus d1 LD Q1 Q2 is equal to 0, right? So that's an example of a discrete Euler-Lagrange equation. And you can interpret that as implicitly defining this map from Q0, Q1 to Q1, Q2, because it implicitly tells you what Q2 is in terms of Q0 and Q1. Okay, and the claim then is that this discrete Lagrangian map, which I defined, it's like by just making this diagram commute in terms of all these discrete Legendre transforms, that map is going to be equivalent to discrete Euler-Lagrange flow. So that's basically what we want to show. Okay, so yeah, okay, so this map from thing to itself is equivalent to the discrete Euler-Lagrange flow. Okay, all right, why is that? Okay, so so let's see. So maybe here it's helpful to copy down what the Legendre transforms do. F plus LD Q0 Q1 is Q1 D2 LD Q0 Q1. And then F minus LD Q0 Q1 is Q0 minus D1 LD Q0 Q1. All right, okay, so, and then this is the discrete Lagrange equation. So I want to look at this map, FLD, okay, which is defined in terms of these two discrete Legendre transforms. All right, so let's just write down, it's like what this condition has to be, right? So it just basically is saying that these three things are related by these two maps, okay? All right, so let's just write down the obvious thing. So that's saying that Q1 P1 is equal to F plus LD Q0 Q1. Okay, and then let's look at the definition of that. So that's equal to Q1 D2 LD Q0 Q1. All right, it's also saying that Q1 P1 is equal to F minus LD Q1 Q2, which is equal to Q1 minus D1 LD Q0 Q1. But of course, these two are the same, right? So those two are equal, and so it means that these two things are equal. So that's saying that D2 LD Q0 Q1 is equal to minus D1 LD Q0 Q1. And obviously that condition is equivalent to the discrete Lagrange equation. Okay. So what that tells you then is that this map, this FLD map from Q0 Q1 to Q1 Q2 is equivalent to the flow of discrete Euler-Lagrange equations. All right, so that's nice. Okay, so then we want to look at this map, FLD tilde. Okay, so then there's we have the discrete Hamiltonian map. I called F tilde LD, and it's defined to be, again, whatever is necessary to make this diagram commute. Okay, so so I need to go up this way first and then down, right? So I first apply F minus LD inverse, and then I compose it with F plus LD. All right, so that's what I'm calling the discrete Hamiltonian map. Right, is a map from T star Q to itself. Okay, and so let's see what that is. Okay, and then we're going to show that we're going to write that map down. And we're going to show that it's symplectic. Okay. All right, I'm going to try to erase just this piece here. Okay, and then I'm going to relabel everything. Okay, so this is 0, 0, 1, 1, 0, 1. Okay, and the reason I'm doing that obviously is because I want to keep that part of the diagram so that I can write down the conditions for that. Okay, so that's saying that Q. Okay, so let's write down what this is saying. So this is saying that Q0 P0 is equal to F minus LD Q0 Q1. F minus LD is given by this, so it's Q0 minus D1 LD Q0 Q1, and Q0, sorry, that's not what I want, right? No, that's right. Okay, so then Q1 P1 is F plus LD Q0 Q1, right? Which is, so this is this relationship. So this is Q1 D2 LD Q0 Q1. Okay, so those two conditions together give me this system of equations. It says that P0 is equal to minus D1 LD Q0 Q1, and P1 is equal to D2 LD Q0 Q1. And this implicitly defines, if you will, a map from Q0 P0 to Q1 P1. And if you know something about Hamiltonian mechanics, it's like then you'll realize that this is really the equation for a, or this is the characterization, if you will, of a symplectic map in terms of a what is known as a type 1 generating function. So as it turns out, this discrete Lagrangian LD is a type 1 generating function. Okay. So this is the characterization, if you will, of a symplectic map in terms of a type 1 generating function. And in particular, LD is a type 1 generating function, right? So LD is a type 1 generating function of a symplectic map. Okay, all right. So that's if you know something about symplectic maps in terms of generating functions. If you don't, it's like you can also sort of very directly show that this map is symplectic. And the way you do this is that you take the second exterior derivative of the discrete Lagrangian. And of course, you know that every time you do the second exterior derivative of anything, it vanishes. So let's see what happens, right? So this is saying that 0 is the second exterior derivative of the discrete Lagrangian. Okay, let's evaluate it at Q0, Q1. So this is, of course, the exterior derivative of the exterior derivative of LD, and I can evaluate what the exterior derivative of LD is. This is D1 LD Q0 Q1. I've differentiated respect to Q0, so there's a dQ0 here, plus D2 LD Q0 Q1 dQ1. All right, so now you use, it's like the map F tilde LD, which is this two equations, and you identify these entries as being related to the momentum. Okay, so now I've applied, it's like the definition of the map F tilde LD. So this is going to be D of minus P0 dQ0 plus P1 dQ1. And of course, the exterior derivative of this is, it's like the P0 wedge dQ0 plus, well, sorry, minus the P0 wedge dQ0 plus the P1 wedge dQ1. Okay, and this is up to assign the symplectic structure, is the difference of the symplectic structure, the canonical symplectic structure at 2 different points, and that's equal to 0. And so that's telling you that the pullback of the symplectic form by this F tilde LD map is the symplectic form itself. So this implies that F tilde LD pullback of omega is omega, which is to say that this map is symplectic, right? So F tilde LD is symplectic. Okay, and then more or less what happens is that you can then show that the discrete Euler-Lagrange flow map is symplectic with respect to the pullback symplectic structure, just because of that commutative diagram which we talked about before. Okay, so let me just stop here for now, and we'll sort of keep going. It's like in a little bit.